Hello everyone, in this video we will explain, Monika and I, the main concepts of a quantum computer and its advantage compared to a classical computer. To begin with, what is the main difference between a classical computer and a quantum computer? Quantum computers are based on a completely different principle than classical computers. A classical computer works with bits. A bit can take the value 0 or the value 1. It is by creating string of bits, string of 0 and 1, that a computer communicates. A quantum computer does not use bits but quantum bits. This is what makes all the difference. A quantum bit is not limited to two values, the 0 and the 1, but it can also enter in phase of quantum superposition, when it combines the two states. So it can take the value 0 and 1 simultaneously. This is why you represent the quantum bit as a sphere. On the screen, you can see the representation of a quantum bit. The 0 and 1 states are located at the end of the z-axis. All possible points on the surface of the sphere are possible states of the qubits. Also, qubits have a second interesting property. They can interact with several, so that their value is intricate. That is to say, linked to each other. If we know a value, we know the property of the others. This is called quantum entanglement, a property unique to quantum computers, which brings many advantages. These two properties, quantum superposition and quantum entanglement, offer incredible possibilities to quantum computers. Let's take a simple example. With bits, calculating the string 001 takes 3 bits. Calculating the 8 possibilities, so 001, 000, etc. until 111, requires 8 uses of the 3 bits. But with quantum bits, calculating the 8 possible strings takes only one shot to the 3 qubits, thanks to the two properties we were talking about before, so quantum superposition and quantum entanglement. So it allows to process a lot of information much faster than with the classical computer. Now, let's see how to use these qubits. So to change the value of a qubit, we use quantum gates. Visually, these gates allow us to move the state of the qubit on the surface of the sphere. On the picture on the right, we have the example of a qubit going from the O state to the plus state thanks to the Hadamard gate. By using several gates together, on several qubits, we create a quantum program that we call a circuit. On the left, we can see a very simple circuit composed only of a qubit in the O state at the beginning, passing through a Hadamard gate. This makes the qubit go from the O state to the plus state. The results of this circuit are presented in the histogram on the right. When we calculate the result of the circuit, the qubit, which is in quantum superposition until then, so somewhere between 0 and 1, takes the value 0 or 1. This is why, when we use a quantum circuit, we have to execute it several times to observe a tendency, which will be our result. Here, the plus state has a 50% chance to tend towards the state 0 or the state 1.
In this project, we learned some important quantum algorithms, namely Bernstein-Vazirani algorithm, Shor's algorithm, and Grover's algorithm. We chose to implement Grover's algorithm for our project. Grover's algorithm is one of the most powerful quantum algorithms that is used to search in an unsorted database. For example, as you can see, looking for a specific number W in an unsorted list of n numbers. While classical algorithm needs n searches, the quantum algorithm needs only square root of n searches, so it provides us with a quadratic speedup. In our project, we used this algorithm to search for number 13 or binary 1101. In this slide, you can see the full Grover circuit that was implemented. The two main parts are the oracle and the diffuser. The best result is obtained when we repeat these two parts with oracle and diffuser approximately pi divided by 4 times square root of n times. For our case, with a 4-qubit circuit, this number is equal to 3. We tested this circuit with both the simulator and quantum computer. Let's see what results we obtained. This is the result that we obtained with IBM's QSM simulator with one iteration of the oracle and the diffuser. It shows that number 13 has the highest probability, 48% to be exact, to occur. That means our quantum circuit successfully detects number 13. And this is the result with 3 iterations of the oracle and the diffuser. It detects number 13 with a higher probability, 96% to be exact. This is the highest probability possible to detect number 13 with Grover's algorithm. Finally, this is the outcome when we tested our circuit in one of the IBM's computers, IBM Q Qto, As you can see, the number we are looking for still has higher probability than the other numbers, but the overall plot is not so nice as the simulation due to errors. So here are some final remarks that we want to conclude with. The first one is a quantum circuit can be implemented to search for any 4-bit number, so any number from 0 to 16 in decimal. Also, due to high noise errors in real quantum computers, such implementation have good results only with one iteration of Grover's operator, that means with Oracle and diffuser. So we would like to thank Pra's team of HPC for making this platform. We also acknowledge the constant support and guidance of our mentor, Mr. G.D. Tomsala, to make this work possible.